So let's begin our first section. We're introducing covalent bonds. We know that covalent bonds are the result of sharing a pair of electrons between two atoms that literally overlap their orbitals. When we think about shared pairs, what we're looking at is investigating those valence electrons in the outermost energy level and letting them overlap their orbitals. So we're being asked to draw a shared pair of electrons between hydrogen atoms. Notice that you would begin by simply writing an electron dot to represent the one valence electron from hydrogen. We know he has one valence electron because he lives in group 1A. I also remember that hydrogen, even though he's in group 1A, where all of the other alkali metals are, hydrogen is a non-metal through and through. That he's placed in group 1A, even though he's a non-metal, to represent his one valence electron. So he has one dot. Now, clearly, his noble gas would be, in the end of the row, would be helium. The noble gas that hydrogen would like to become would be helium's configuration of 1s2. Hydrogen is very unstable with one valence electron. Knowing that it could create a shell resembling a helium, that it would be isoelectronic with helium by sharing a pair of electrons, and that's exactly what it does. By combining, and combining means sharing the pair of electrons, each hydrogen now has two representing the configuration of helium. So let's keep in mind what I'm saying. I'm going to draw a circle around the hydrogen, and that hydrogen on the right has two electrons. It just happens to be sharing them with the hydrogen on the left. This right here, this overlapping area, represents a shared pair of electrons. Overlapping, probably has two p's. Overlapping shared pair is a single covalent bond. And when I count those for each atom, those electrons inside the circle count for both. So a shared pair between the two hydrogens gives each hydrogen two electrons to achieve the noble gas configuration of helium. So this covalent bond is two electrons, right? A pair of electrons in which those bonding atoms actually share two electrons for a single covalent bond. This is the definition of a molecule. The molecule is the biggest, discrete group of atoms held together by covalent bonds. The elemental form of hydrogen is a molecule built of two hydrogen atoms sharing one pair of electrons. So the shared pair of electrons between two hydrogen atoms is easy as showing a line connecting the two dots, a single covalent bond. Hydrogen is a diatomic molecule, just as we had listed. There are actually 7 naturally occurring diatomic molecules that we should put into our notes. Hydrogen was just one of those. And I'll redraw that. Hydrogen with its one valence electron combines with the second hydrogen and its one valence electron, forming a molecule of H2. Hydrogen is a diatomic molecule in its elemental form. It's just one of 7. Let's investigate the others. For example, let's go into the halogens and we'll see something that is very similar. Now remember, hydrogen is the nonmetal in group 1A. The halogens are those nonmetals in group 7A. So they'll have 7 valence electrons, such as fluorine. Fluorine with its 7 valence electrons. Obviously, it's very unstable with this unbonded electron, so it needs to form an octet to create stability. Notice that if it binds or bonds or combines with another fluorine in a shared pair, now each of those has 8 valence electrons. Remember how we count those? A shared pair counts in both directions. So now the fluorine has the noble gas configuration of neon with an S2P6 configuration. An 8 octet has been achieved by sharing one pair of electrons. So fluorine is also a diatomic molecule. Think of underneath that, you have chlorine. There's going to be a periodic trend. Chlorine with its 7 valence electrons will form a single covalent bond, forming a molecule of chlorine. Chlorine is also a diatomic molecule. And you can see that when they share a pair of electrons, each atom now has the 8 electrons it would like to have. And what happens to chlorine when it shares a pair? It becomes like argon with its S2P6 configuration, 8 valence electrons. Underneath chlorine lives bromine. Bromine also has 7 valence electrons. Are you drawing these with me? You should be. Put these into your notes. Bromine is a diatomic molecule, and so when I see its shared pair, I can now see 8 electrons around the bromine. It has now become like krypton. And krypton with its S2P6 configuration, giving bromine 8 valence electrons by sharing a pair of electrons. And one more in this group is iodine. Iodine has 7 valence electrons. It lives in group 7A. It is an unstable configuration by itself, so in nature it will help stabilize itself by just bonding to another like atom, making sure that the shared pair of electrons between the two gives its noble gas configuration, such as xenon with its S2P6, 8 valence electrons. So 7 electrons in the halogen will share one pair of electrons, so each atom now has a combined number of 8 electrons. Sharing electrons allows those molecules in nature to become much more stable. We said that there were 7 naturally occurring diatomic elements. We've shown you 5 so far. Let's go to group 6A, and I'll show you the next one. Group 6A, we're going to find oxygen. Now, oxygen is a gas at room temperature, and so when we draw its 6 valence electrons, I'm just going to draw 1, 2, 3, 4, 5, 6. We can clearly see that it is unstable because it does not have its octet. Now, when I draw another oxygen, because I know it's going to be diatomic, I can see a site here where those 2 oxygen atoms can combine. And that's a first single covalent bond. But I still notice that this oxygen has a lonely electron over here, and this oxygen has a lonely electron over here. When this happens, the atoms are able to combine those electrons. Remember, they're not stationary. Our little dot symbols suggest that they're stationary, but they're not. Electrons are moving very quickly around the nucleus of an atom. So they bring them between and make a second shared pair of electrons. Now let me redraw that much cleaner. We have an oxygen with 2 lone pairs combined with another oxygen who has 2 lone pairs, and they're sharing 2 pairs, which makes this a double covalent bond. The oxygen molecule in nature is the elemental form of oxygen. We find it always combined, and in an elemental form it will be O2. It's just oxygen will have a double bond, so that when I count, oxygen and this oxygen are sharing 4 electrons. 2 pairs of electrons are being shared for a double covalent bond. And I still count 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons around each of those oxygens. So oxygen is a naturally occurring diatomic molecule existing with a double bond. That's 6 of the 7. Who else? There's one more, and that's an element in group 5A. That's nitrogen. Matter of fact, I think I'm going to just give myself more room. Let me take that out, make sure I don't squish things in. Let's bring it down and give it its own space. So I'm going to talk about nitrogen next, group 5A. Nitrogen must have 5 valence electrons We know that because it lives in group 5A. Now, group 5A with its 5 valence electrons really wants to have 8, right? The octet rule. So when I redraw, I can see that I have one set of shared pair of electrons between those lone pair there. And I can see that these two can come up in the center to make a second shared pair. And I'm going to bring these guys into the center and draw a third shared pair of electrons. Think about that. If 8 is the magic number that all the atoms would like to have, nitrogen has 5 valence electrons. It's going to need 3 more, 3 shared pairs of electrons. So let's clean that up. This is too messy. This is my workspace, but this is the final answer where you see nitrogen with a triple covalent bond. 3 shared pairs of electrons. So that means 3 lines between the elemental symbols. 3 pairs of electrons being shared. And how I count that, remember a triple bond being shared gives 2, 4, 6, 8 to the nitrogen on the left, 2, 4, 6, 8 to the nitrogens on the right, and we have an octet for both atoms. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are the 7 elements in nature that exists as diatomic elements. Their elemental form is a molecule, not a single atom. There's a little sentence I use to help me remember this. A little sentence that's funny. It says, horses need oats for clear brown eyes. And of course, eyes is for iodine. Horses need oats for clear brown eyes helps me to memorize the 7 elements in nature that exist as diatomic molecules. Memorize those. All right, so we've introduced quite a bit there. We've talked about shared pairs of electrons. We've talked about single, double, and triple bonds. Let's take some next steps and catch the notes up to what we've been practicing with those diatomic molecules. A quick sip of coffee there. We have some unshared electron pairs that are called non-bonded electron pairs, or just simply lone pairs. So if I draw an example, hydrogen with its 1 valence electron, I'll draw next to it fluorine, who lives in group 7A, so I know it has 7 valence electrons. And I can see when I combine these two to make a single bond, that each has now obtained a noble gas configuration. Remember how we count that? Hydrogen, who wants to be like helium, has 2 valence electrons. So it is now like helium. And when I think about counting for this guy, it has 8 valence electrons. 8 valence electrons. Its noble gas configuration is now like neon. So each has achieved a noble gas configuration. Hydrogen, of course, only needs 2 to become its noble gas of helium. And fluorine gained 1 to become its noble gas like neon. Here's the vocabulary. We're looking at, on fluorine, 3 sets of dots that are not bonded, non-bonding pairs. And this really plays a role when we determine molecular geometry as well. The non-bonding pairs end up as dots. Not involved in bonds are non-bonding pairs. Fluorine has 3 pairs that are non-bonding. It has 1 set of bonded and 3 lone pairs. So that's how we're counting. Shared pairs involve in a bond, and the lone pairs are left as dots. Remember, hydrogen shares 2 electrons with the goal of becoming helium. Fluorine shared 1 pair with its own 3 sets of dots until it became like neon. So they want to become like the noble gas that's closest to them in the periodic table. So hydrogen is unique because of its only, it only needs 2 electrons to fill its first energy level. It has no more electrons. So if this is hydrogen, its goal is to become like helium. That first energy level is filled with 2 electrons in the s sublevel. But anything bigger than that, we know that we want to achieve the octet, just like fluorine did. By gaining 1 more electron, it became like neon, and so forth. So as we drew the hydrogen and fluorine dot structures, including all the lone pairs, that's all I did right there for you. We're looking at H combining with an F. Hydrogen has no lone pairs because it's just 1 shared pair to become helium. Fluorine with its 3 lone pairs and 1 single bond became like neon. Use the electron dot symbols to show a hydrogen atom and a chlorine atom, and we'll do this as a little example. So as we think about hydrogen living in group 1A, we know that it has 1 valence electron. And when we find chlorine, we see that it is in group 7A, so we know it has 7 valence electrons. So I see hydrogen with its 1 dot, and I see chlorine with its 7 dots. And see how I'm going to just make sure that I put the lone empty partner here next to the hydrogen. And to show a shared pair of electrons, I'm just going to connect those dots, and that represents a single covalent bond. This is a diatomic molecule because it's built of 2 atoms, but they're just different atoms. They're heteroatoms. One's a hydrogen, one is a chlorine. So HCl has 1 single bond, S-I-N-G-L-E, single bond. And on the chlorine, we see 3 lone pairs of electrons as well. Counting, chlorine now has 8 valence electrons. Hydrogen has 2 valence electrons. Hydrogen has become like helium in its count, and chlorine has become like argon with its count, the noble gas configurations of noble gases. When we begin drawing these, we've been practicing what are called Lewis structures. These are electron dot structures for molecules. So we can make dot structures for atoms, and we can combine atoms to make molecules and represent their bonding using a Lewis structure. And the goal here as we begin drawing Lewis dot structures is to satisfy the octet rule for all of the atoms, except hydrogen, who only needs 2 to be a satisfied noble gas. And we're going to go through some examples and kind of just share what they look like and start building some in a logical order. So here we have a molecule that I wanted to draw called methane. When we think about making a molecule and showing it in a Lewis dot structure, we always build around a central atom. And we're going to practice these steps over and over and over, but let me just say we want to select a central atom. And when I mean that, it's going to be in the center and all of the other atoms combine back to it. We're going to learn when we select a central atom to pick the least electronegative element, which is the same as saying pick the one that's farthest from fluorine, but never pick hydrogen, because hydrogen only forms 1 bond and then you're stuck with just 1 bond. So hydrogen is never a good choice for the center. We'll also learn that halogens are never a good choice for the center because they also only form 1 bond. So when I place carbon in the center of a molecule of carbon and 4 H's, the goal is to see these molecules as symmetrical. Now notice, let me just back that up. Carbon has 4 valence electrons. It lives in group 4A. All right, so I can see what I'm coming up with the 4 dots. Since carbon lives in group 4A, 4 valence electrons, and I get a visual right away that there's 4 spots open for bonding, right? Those lonely electrons around the carbon are seeking another electron. And we know that hydrogen with its group 1A has 1 valence electron. And so I can satisfy hydrogen by connecting to each of these lone pairs and creating single bonds in all directions. This is a molecule known as methane, CH4, the simplest hydrocarbon in organic chemistry. Now remember, semester 2, there's a lot of organic chemistry where we investigate carbon chains. I also want us to just take a moment and notice the way that I drew this in this Lewis structure. I might be fooled into thinking this is a flat molecule on a piece of paper with a 90-degree bond angle. It is not. If you build this molecule with your molecular model kit, you would notice that it's not a 90-degree bond, that it's not lying flat on a plane, but it actually has a three-dimensional shape to it. And that's what we can get an idea of here. Here's our carbon atom coming straight out of the page there. With leading up is a hydrogen, going behind the page, coming out of the page, going behind the page. That those atoms themselves are not looking like a right angle. So we're going to learn that to represent this, I can place a carbon attached to a hydrogen in the same plane, attached to hydrogen in the same plane, and we'll see like this wedge coming out of the plane and a dash going behind the plane. Think of that as a piece of paper, if you will. That's going to be the representation of the true molecular geometry of this particular molecule when we get that far. That the bond angles we'll learn are actually 109 degrees, 109.5 degrees in a tetrahedral shape. That's our direction of our chapter, is to realize Lewis dot structures are great for showing us connectivity, but it's not necessarily great at showing us molecular geometry. And that's kind of being both challenges in our chapters to think, okay, I can connect them. Now what do they really look like in space? Here's another example, ammonia. Of NH3. Now I'm going to select the central atom of nitrogen, and when I do so, nitrogen has 5 valence electrons. And I can see now, when I place 5 dots around the nitrogen, that it has 3 open spots for bonding. And that's exactly what happens, that the nitrogen will combine with 3 hydrogens so that everybody has an octet. When I draw the Lewis structure, I notice a lone pair on top of the nitrogen, one set of dots that are not involved in bonding. We'll learn how to read our Vesper chart, that when we have the central atom leading to 3 atoms and 1 lone pair, that we're going to learn to call this trigonal pyramidal. It doesn't look like a flat object on a piece of paper. But when I build it, the ammonia molecule represents a shape in space. That the nitrogen, with its electrons up high, and leads down to, and just kind of use this spatial arrangement again, there's a hydrogen. Here, this one's coming out of the page. This one is going behind the page. That these objects have 3-dimensional shapes to them. Look at this as kind of the base of a pyramid, all sitting flat on the tabletop like a base, just like up here. These are sitting flat on the tabletop, but except this guy has something coming up high. Well, this guy has a big electron cloud up there, trigonal pyramidal. We'll learn to call tetrahedral, and trigonal pyramidal. Coming our way, we're just throwing out words now. And one more to investigate here. This is a water molecule. Water, of course, has oxygen in the center. Now, one of the things that we're all used to doing is combining the oxygen to hydrogen. And in doing so, we think that this looks like a very linear molecule. We might even think that this looks like a 180-degree straight line across when I look at the hydrogens coming out of the oxygen. But that is not the shape of the molecule at all. The Lewis dot shows us the connectivity, but then we have to take it a next step and think about what does it look like really as a 3-dimensional object. The valence shell electron pair repulsion theory says, you know, oxygen with its 2 sets of dots that are not bonded, they want to be spatially as far apart from each other as possible. And we can do so by maximizing the bond angle and make this between them about 105 degrees, giving these guys as much space as possible to, kind of spread out. Those electron dots are like charges, and they want to make sure they're spread out as far apart as possible. So we will see that when this molecule of water, the oxygen has two sets of atoms it leads to, those are the hydrogens, and two lone pairs of electrons that are not bonded, we'll learn how to read our VSEPR chart and know that this is actually called a bent molecular geometry. That water is not correctly drawn as a linear molecule, but in nature it is a bent molecule, and it does so to make sure that it gives as much space as possible to these unbonded pairs of electrons. Now, I just taught you all the sections at once, but this is kind of challenging us to think, okay, step one, let's get a Lewis dot structure drawn. And then, okay, now I understand how they're connected, but what does it really look like in space? These molecules aren't flat, just laying on a paper, but they have shapes to them, and we have to investigate what they look like in space as well. So we're introducing covalent bonding, and as it's related to the periodic table. We know that they're formed when two nonmetals combine, or when a metalloid and a nonmetal combine. So thinking about nonmetal to nonmetal, we really don't have too many elements on the nonmetal side of our border. So we're just looking at how they combine to form molecules. And it begins just kind of investigating how many bonds each atom would like to have. So let's write these out together. And what we're going to do is just investigate how many bonds would it need to satisfy its octet. Alrighty, so the first one in our box there, it says hydrogen. I want us to investigate the hydrogen atom has one valence electron. So with its one valence electron, and I know that because it lives where it lives, it would like to have a noble gas configuration of helium. So I can clearly see that hydrogen would like to form one bond. And that's what I want us to just realize. How many bonds and how many lone pairs for each element? Well, hydrogen is going to want to form one bond and have no lone pairs. That's its trend to become like helium. Let's move over one and go to boron, the next nonmetal. Boron we'd call a metalloid. Boron. Now boron, who lives in group 3A, when I write its elemental symbol, we're going to see boron with 3 dots. Alrighty. With its 3 dots, how many would it like to have? How many bonds and lone pairs are likely? Well, boron with its 3 dots only has room for 3 bonds. And when I draw that out, kind of thinking about what it would look like, its 3 bonds will end up looking like an equilateral triangle when we add in the VSEPR theory, the molecular geometry. 3 bonds and no dots. Well, I'll put no lone pairs. We'll learn that this is one of those exceptions to the octet rule because it does not have 8 electrons around it. It will only have 6, and that's okay because it lives in group 3A. It only has 3 dots. It only has 3 spots for bonding. That's why we'll call it an exception to the octet rule. Let's go over to carbon next. Carbon, who lives in group 4A, we place its electron dots, one around each side. There's the electron dot symbol for carbon as an atom. Well, now I can see that carbon itself has 4 open spots for bonding. So when I write out how many bonds it's likely to have, it's going to have 4 bonds. And I'm kind of getting us used to the idea that they're not just 90 degrees, that these are going to have shape. But 4 bonds are going to be happening for a carbon. That's its goal, is to have 4 bonds. And of course, then it will have no lone pairs. There are no dots left. Each one is going to be connected to something else. Let's keep going. I'm going to come down here and do nitrogen. Nitrogen, who lives in group 5A. So now I can see nitrogen with its 5 valence electrons. Alrighty. Now that's a visual for us to use, that it only has 3 spots for bonding. So when I redraw and kind of think about what it would look like for drawing, for bonding, I can see 3 bonds and 1 lone pair. So that this lone pair up here plus 3 more bonds gives it the 8 electrons to obey the octet rule. Let's look at oxygen. Oxygen lives in group 6A. So it's going to have 6 valence electrons. When I think about what is it going to take to get oxygen 8 electrons, I can see that oxygen, with its 2 empty open spots there, are going to form 2 bonds and keep 2 lone pairs. When I look at fluorine next, fluorine, who lives in group 7A, we can see fluorine with its 7 valence electrons. Clearly I can see that in order to achieve an octet, the fluorine wants to form 1 bond, 1 shared pair. So we'd have 1 bond only for any of the halogens and 3 sets of lone pairs. And finally, to just wrap up that period 2, we'll look at neon. Neon, of course, is in group 8A. And so when I think of neon, does it even want to form any bonds, or is it the envy already of all of the elements up there? So there's just no empty spots open for bonding, 0 bonds, and 4 lone pairs. So we've investigated period 2, all of the non-metals, plus hydrogen really, but period 2 we did hydrogen with its 1 valence electron forming 1 bond only. Boron, with 3 valence electrons, had 3 bonds. Carbon, with 4 valence electrons, wanted 4 bonds. Nitrogen, with its 5 valence electrons, 3 bonds and 1 lone pair. Oxygen then had 6 dots, 2 bonds and 2 lone pairs. The halogens would have 7 dots, so that's 1 bond to 3 lone pairs, and those halogens all follow that same trend. And then of course the noble gases, no bonding and 8 dots. That's going to help us predict how to put atoms together to form compounds, these molecular compounds that satisfy the octet. We get a feel for how many dots and how many bonds each one of these atoms in the columns they represent will need. And that was the purpose of investigating how many dots, how many bonds for the elements based on their number of valence electrons. So what does this mean? Can we apply a periodic trend to determine how many bonds and how many lone pairs are predicted for these examples? I want you to find the group number they live in and represent their Lewis dot. So for example, when you find silicon, its elemental symbol Si, do you see it right below carbon? Which means it's in group 4A. So if I were to draw silicon, it's going to resemble our example of carbon, isn't it? With 4 valence electrons, I can see that it will have room to form 4 bonds and have no lone pairs. Here's bromine. Bromine has the elemental symbol Br. Do you see how it's in group 7A? It's part of the halogens. So when I draw bromine's electron dot symbol, it has 7 electrons around its symbol. Clearly I can see that it would like to have 8, so that gives me 1 bond and 3 lone pairs. Let's try sulfur. Sulfur, elemental symbol S, and it lives in group 6A. It's right under the oxygen. So if I were to draw sulfur, it will have similar properties than that of oxygen. 6 dots. I can see 2 open spots for bonding, so I would predict 2 bonds and 2 lone pairs to give it the octet. And finally, phosphorus. Phosphorus is the elemental symbol P. It's in group 5A, just like nitrogen. Phosphorus with its 5 valence electrons. I can see 3 open spots for bonding. And it has 1 lone pair. So that's the challenge there, is just trying to recognize how many bonds, how many lone pairs, with the goal of getting these atoms to an octet, except for hydrogen, who only wants 2 electrons to be like helium. Let's try another application to this, filling in the lone pairs of atoms for every main group element, except hydrogen, of course, to give it an octet. I'm going to redraw these. Here's an H connected to a carbon, H, Cl. You see, what we're asking is to find how many dots would we need on anything that's missing them. Well, hydrogen lives in group 1A, so it only has 1 dot. We realized it only has 1 spot for bonding. No dots ever around hydrogen, so it's done. Carbon lives in group 4A, and so we said carbon wants to have 4 bonds, and it clearly does, so there's no dots there. However, chlorine lives in group 7A with 7 valence electrons. It had room for 1 bond. What it's missing are its dots. Attack it this way as well. Hydrogen, 1 bond. It is completely satisfied. We know hydrogen only wants to have 1 bond. The carbon, it wants to have 4 bonds, and clearly when I look out, each carbon to hydrogen here has 4 bonds, so that's good. But when I encircle the chlorine, I can see that it's missing an octet. So to finally answer that, you just need to place 3 sets of dots around the chlorine, and then everybody has the 8 electrons it needs. When I investigate hydrogen, it only needs 1 bond. Hydrogen will never get dots. So that's always off the plate. Hydrogen, never any dots. The nitrogen, who lives in group 5A, right now the nitrogen has only 3 bonds. A moment ago we said nitrogen in group 5A, it has spots for 3 bonds, but to complete its octet, it needs a set of dots up there. Now it has 8 electrons. Next door to that is oxygen. We said oxygen lives in group 6A. There's its 6 dots. It has room for 2 bonds, which I can see there, but it's missing its lone pairs. Letter C. Hydrogen, never any dots. Carbon, it has room for 4 bonds. It has them. No lone pairs on the carbon. The oxygen, we said 2 electron bonds and 2 sets of dots. So with the carbon, the oxygen needed, with letter C, I mean the carbon needed the oxygen. In letter C, the oxygen needs 2 sets of dots. And what's going on with D? Looks like hydrogens are good. Carbon has 4 bonds, but these halogens, the bromine, they'll need their set of electrons to complete the octet, knowing that bromine in group 7A had 7 valence electrons, we said halogens need 1 bond and 3 sets of dots. So complete the dots around the bromine and you'll have all of those atoms having a complete octet. Whew, we did it. Hi everyone, Mrs. Hanson once again. Hey, we're going to pick up some lessons with Lewis dot structures in 4.2, beginning with the definition of a molecular formula. Once and again, we know that it shows the number and identity of all the atoms in a compound. But what it lacks really is just not showing us the connectivity of how the atoms are bonded to one another. So for example, if I were to tell you we had a molecular formula of C2H6, you would know that there are 2 carbons and 2 hydrogens in that molecule, but you really wouldn't know how they're connected together. And that's a huge advantage when we see a Lewis structure, because now it's going to show us the connectivity between the atoms as well as all of those bonding and non-bonding valence electrons. That when I start to see the carbons connected together and that each carbon is going to complete its 4 bond requirement by placing all of those hydrogens attached to it, we now can see a Lewis structure for the molecule, knowing that I see a carbon-to-carbon single bond, and I notice that each carbon has 3 hydrogens attached to it. And so that's the advantage really of a Lewis structure, is showing connectivity. What we also will involve ourselves with, and just kind of thinking about what's coming here, we're going to be involved in the Vesper theory in a few sections from now, in which we start thinking about molecules as these 3-dimensional objects. In addition to how they're connected, we'll get an idea of what their geometry is as well. And that we'll learn that a carbon with its 4 bonds will have a molecular geometry known as tetrahedral. Tetrahedral is not spelled right. I'll just say it, tetrahedral. And you'll have an idea that it looks like a tetrahedron with bond angles of 109.5, all coming our way as we begin. But, first steps, let's go through these guidelines for drawing Lewis structures. How do I create a Lewis structure? And then we're going to practice in this section. So, first step in creating a Lewis dot structure is to count up how many total number of valence electrons we have in a compound. Now what I mean by that is, a moment ago we drew methane, CH4. I know that carbon, who lives in group 4A, has 4 valence electrons. I know that hydrogen, who lives in group 1A, has 1 valence electron. But knowing that there's 4 hydrogens in the compound, I know that there'd be 4 total dots, if you will, coming from hydrogen. There would be 8 valence electrons in a methane molecule. Count up the total number of valence electrons. How many dots do we get to play with? Number 2 says we're going to select a central atom, which is always the least electronegative element. Now, we have yet to define electronegativity, but I can just share with you, it's the ability of an atom to draw electrons towards itself in a shared pair, in a bond. Fluorine, we'll know, is the most electronegative element. It's the strongest of strong nonmetal. And because fluorine is in the top right of our periodic table, the least electronegative would be the furthest away. And we said never put hydrogen or a halogen in the center because it only gets 1 bond. And since we have to attach all of these atoms back to the central atom, don't pick an atom to be the central. It only has 1 bonding opportunity. We'll then learn to connect back all the other atoms to the central atom using a single bond. And as we practice, we'll say, okay, carbon will be in the center, and I'm going to attach back all of the other atoms to the central atom. Never, ever start creating these linear attachments, right? It just doesn't work that way. Instead, we attach back to a central atom, and we always think symmetry. Let symmetry guide you through your selections. After we connect back to the central atom, we're going to fill the octet of all of those outer atoms. Again, tallying the electrons. If we run out to fill the central atom, we kind of consider a double bond or a multiple bond. And I wanted to do some examples with you just so that you can look at these rules and actually employ them. And the first one we did was methane, CH4. But let me go through that step by step again. Step 1, tally your electrons. And what I mean by that is how many dots do we get to play with, right? How many dots, no more nor less, do I have to make my molecule with? We said since carbon lives in group 4A, it's going to have 4 valence electrons. Since hydrogen lives in group 1A, we have 1 valence electron, but there's a total of 4 hydrogens in the compound, so 4 dots. That means we get 8 electrons total to build our molecule, step 1. Step 2 said select the least electronegative element, the farthest from fluorine, and put it in the center. Well, here, if we're not allowed to use hydrogen, clearly we see carbon is in the center. Next thing I do is attach back all of the other atoms, which are all 4 hydrogens, to the central atom, and then retally. Remember, each shared pair is 2 electrons, so we used 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons were done. Now what's nice is with this very first simple example, we drew a molecule that very quite simply satisfied the octet. I ran out of electrons, all done. So with our methane molecule, we'll learn that the carbon attached to those 4 hydrogens has a molecular geometry known as tetrahedral. And that those bond angles are going to be 109.5 degrees away from each other. A tetrahedral atom, not a 90 degree like our Lewis dot structure suggests, but a carbon attached to 4 other atoms is a tetrahedral shape. Let's consider a next example, and I'll just work down the page there with those examples for you. Notice the next one on your worksheet says PCl3. Phosphorus trichloride. Let's count how many total electrons we have. So tally your electrons. Phosphorus, who lives in group 5A, it's going to be able to contribute 5 electrons, 5 dots in my structure. Chlorine, who lives in group 7A, contributes 7 valence electrons. But do you see how there's 3 of them in the formula? So the total number of dots, total number of electrons from chlorine will be 21. When I sum those, I get 26 electrons to play with. No more, no less, I get 26. Step 2 says, select a central atom and place it in the center. Select your central atom. Never pick a halogen like chlorine because it only has room for 1 bond and you run out of stuff to do with it quickly. Phosphorus is the least electronegative. And so when we get this far and define electronegativity, we want to define electronegativity as the ability to draw electrons towards itself the atom's ability to draw electron towards itself in a covalent bond. So we want the least electronegative element, the farthest from fluorine, the least likely to be able to pull electron density towards itself. And clearly you can see that that's phosphorus. Phosphorus will go in the center. And I'll tell you, instinctively, you're always going to know to be able to pick, just think symmetrical. Symmetry, phosphorus in the center, and I can see attachments of chlorines going back. Step 2, we selected the least electronegative element, so we have the central atom. Step number 3, attach back all of the other atoms. So when I do that, when I attach back, that's chlorine, chlorine, chlorine. Those are the 3 chlorines. I attached them back. And remember to retally. We had 26 electrons we were working with, right? That's what we tallied up here. To create 3 single bonds, we used 1, 2, 3, 4, 5, 6. That leaves us 20 electrons left to place. Step 4, complete the octet of all outer atoms. One, 2, 3, 4, 5, 6, he's done. 7, 8, 9, 10, 11, 12, he's done. 13, 14, 15, 16, 17, 18, he's done. We used 18 electrons to complete the octet of the outer atoms of chlorine. That leaves us 2 more. And that last step says, complete the octet of the central atom. Those 2 get placed on the phosphorus. We've used up out of dots. And we've recognized that all of those atoms now have an octet. Here, the phosphorus, 8 valence electrons. Each chlorine, 8 valence electrons. With 3 single covalent bonds, each now with 8 electrons around it. Phosphorus trichloride will learn. The name PCl3 will learn phosphorus trichloride. Hear the "ide" on the ending? That's coming up in our lessons, how to name these babies. And then we'll also learn that since phosphorus in the central atom has attachments to 3 atoms and 1 lone pair, so just to highlight, it has 1 lone pair and attached to 3 atoms. We'll learn to use our VSEPR chart, valence shell electron pair repulsion, to find its molecular geometry, and we'll learn to call this trigonal pyramidal. And that it really doesn't look like those right angles I drew, that the phosphorus with its lone pair will have a chlorine coming down, a chlorine kind of coming out of the page at you, and a chlorine kind of coming behind the page at you there. And you'll learn that we'll think about these in a 3-dimensional object where those chlorines are the base of a pyramid. What's next to draw? We're going to look at CH5N. All right, CH5N. That's our next example. So this is interesting. We've got CH5N. Again, a molecular formula tells us how many of each we have, but no idea of connectivity. This time when I select the central atom, the least electronegative element, the furthest from fluorine, electronegative, we kind of have to think about who's going to be the central atom. And I know I have to tally the electrons. Just kind of brainstorming my approach. All right. Carbon lives in group 4A. It will contribute 4 dots. Hydrogen lives in group 1A. It contributes 1 dot. But there's 5 of them in the structure, so I'll get a total of 5 dots contributing from the hydrogen. And of course, nitrogen lives in group 5A. So let's add what we have. We get 4, 9, 4. This adds to 14 electrons, 14 dots to build our structure. Alrighty. So thinking about what we know about atoms, I know that carbon is allowed to have 4 bonds. I know that. I know that carbon lives in group 4A. It has room for 4 dots. Alrighty. I also know that nitrogen, who lives in group 5A, will have 1 lone pair and room for 3 bonds. And then hydrogens are always just used as kind of attached back at the end to fill octets, right? It's only allowed one bond. So that's what I'm thinking about as I decide how to connect my atoms together. It makes no sense to put a hydrogen in the center because it cannot have two bonds. I'm not allowed to do that. So it can only go on the outsides of the structure. But what I can do is connect a carbon and a nitrogen and still meet the requirements of how many bonds and how many lone dots it's allowed to have. So thinking that through, when I placed carbon next to nitrogen, I did so because I knew that a hydrogen could not be attached between the two elements. Let's retabulate how many things we've used. We've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 dots. And something magical has happened. We're allowed to just place all of those hydrogens leading to those, leading out from those single bonds. And we've used all 14 electrons. We've satisfied the octet. We've used the hydrogens as like the outside atoms to complete the bond requirements. And really what we let guide us is the discovery that carbon needs 4 bonds, that hydrogen needs 3 bonds and 1 lone pair, and that hydrogen is only allowed 1 bond as it's completing its octet. And we assembled those pieces to create a Lewis dot structure. This will also kind of be fun. We'll talk about the geometry around each particular atom, that we only focus our attention to one central atom at a time when we talk about molecular geometry. We'll learn that since this carbon is attached to 4 atoms, attached to 4 atoms makes it a tetrahedral molecular geometry. We don't know that yet, but we're going to, tetrahedral. And that this nitrogen is attached to 3 atoms and 1 lone pair, so we're learning that that's called trigonal pyramidal. So we have 2 central atoms in that molecule. Let's turn our attention then to the right side of your examples. We've done CH4, we've done PCl3, and we just did CH5N. How about HCN, hydrogen cyanide? Hydrocyanic acid is another word for that. All right, let's tally our electrons. Hydrogen lives in group 1, 1 valence electron. Carbon lives in group 4. Nitrogen lives in group 5. We have just 1 atom of each. That gives us 10 electrons. The least electronegative element will go in the center. That's carbon. We'll attach back all of the other atoms to the central atom. So that carbon is in the center, leading out to nitrogen in one direction, hydrogen to the other. That took a total of 4 dots, right? Because each bond is a pair of electrons. That leaves us 6 electrons. Then the rule says fill the octet of all the outer electrons for all the outer atoms first. Hydrogen never gets any dots. So the 6 electrons go around the nitrogen. And we're out of dots then, aren't we? Clearly you see that the carbon is not yet satisfied. It needs to have 4 bonds. Nitrogen is fine with its, you can see that it has 3 sets of dots and 1 bond. But do you remember what we've learned? Carbon needs 4 bonds. Nitrogen needs 1 set of dots and 3 bonds. Right now our structure is not yet complete. If we were to take 2 sets of dots from nitrogen and bring them together into a shared pair between the between the carbon and nitrogen, we can satisfy the bond requirements of both atoms. If we run out of dots, the direction said, consider a multiple bond. And when you do so, when you consider the multiple bond, we've now got the arrangement of those atoms exactly like we want. In other words, this carbon has the 4 bonds that it requires. One of them is a triple bond and the other is a single, but that still adds to 4 bonds that it requires. The nitrogen needed 3 bonds and a set of dots. It has exactly what it wants. 3 bonds, all involved in a triple bond, still counts as 3 bond requirements and 1 lone pair. We just drew HCN with a triple bond leading out to the nitrogen there. HCN. Let's keep going. This is fun. Carbon lives in group 4A. We have 4 valence electrons. Oxygen lives in group 6A, and there's 2 of them, so we get a total of 12 dots. Then 16 is the sum, 16 dots, no more, no less. The least electronegative element is carbon. It will go in the center. The furthest from fluorine is carbon. I'm going to attach back all of the other atoms to the central atom using single bonds. To do that, we used 1, 2, 3, 4 dots because those are shared pairs. We have 12 dots remaining. Now that says, fill the octet of all of the outer atoms next. We used 12 dots to fill the oxygens. We're out of dots. When you run out of dots and the central atom has not yet achieved a noble gas configuration, consider a multiple bond. In other words, we know carbon wants to have 4 bonds. We know oxygen wants to have 2 bonds and 2 sets of dots. So we get a feel that we're just not done yet. Now I can move a set of dots between each side of the carbon and a shared pair where oxygen is leading to a double bond leading out to the next oxygen. We've met the requirement for each atom. Carbon, 4 bonds, just like it wants to have, involved in double bonds in both directions. The oxygen, 2 sets of dots, 2 bonds, perfect. Oxygen, 2 sets of dots, 2 bonds, perfect. Carbon dioxide places carbon in the center with 2 double bonds in each direction to the oxygen. We'll try another together, CH2O. Carbon lives in group 4A, which is going to contribute 4 electrons. Hydrogen lives in group 1A. Each one of those hydrogens contributes an electron. We'll have 2 coming from hydrogen. And then oxygen, of course, in group 6A has 6 valence electrons. That's 6 and 6, that makes 12 dots. No more, no less, we get to use 12 valence electrons. The least electronegative element goes in the center. Now remember what that means? That's carbon, the farthest from fluorine. Carbon is further from fluorine, so it is least electronegative. That term we'll learn just means the ability to draw electrons towards itself in a shared pair. Fluorine is the strongest of strong nonmetals, pulling electron density towards itself. The farther you move away from fluorine, the weaker the atom becomes at drawing electrons towards itself. Carbon is farther from fluorine than oxygen. That's how I know carbon will be the central atom. We attach back all of the other atoms to the central atom using single bonds. To do that, we used 6 electrons. Remembering, each shared pair is 2 electrons. We have 6 dots left. Fill the octet of all of the outer atoms. That's the oxygen. Hydrogen never gets dots, so we'll fill the oxygen next. We're out of dots. However, clearly we see oxygen wants to have 2 dots, 2 bonds. That's what it would like to have. Carbon needs to have 4 bonds, so we're not done yet. Do you notice carbon doesn't have enough bonds? So when we run out of dots, and the central atom has not yet reached its 8 electrons, that's when you're told to consider the multiple bond. We can take the set of electrons from oxygen and give them to carbon in a shared pair. Now we've achieved 4 bonds around the carbon just like it wants to have. We've achieved each hydrogen's 1 bond just like it wants to have. And we've achieved the oxygen 2 dots, 2 bonds. When I redraw this clean, we'll see that since carbon is attached to 3 atoms, it's attached to an oxygen, it's attached to a hydrogen, it's attached to a hydrogen. That central atom carbon is attached to 3 atoms, that the molecular geometry is now called trigonal planar. It's going to look like an equilateral triangle. We'll learn that when we get to the Vesper theory section of our chapter, we'll see that this truly is an equilateral triangle around the central atom. Equilateral triangles have bond angles of 120 degrees, right? So as I think about the bond angle between the hydrogens, the bond angles between the oxygen, all of those looking like an equilateral triangle. So I'm integrating all kinds of good stuff as we practice. The Vesper theory, bond angles, how to draw Lewis dot structures, kind of being real sneaky and teaching you everything at once so that as we practice, it will become quite easy. It's time for you to practice. Turn off the video for a minute, draw these molecules, come back and compare with me. Don't cheat yourself of the opportunity. It's so important for you to try first, then come back when ready. All right, let's come back. Letter A, HBr. You noted that hydrogen with its 1 valence electron, bromine with its 7 valence electrons, you knew you had 8 to do, 8 dots to do. And this one was so easy. 1 single covalent bond, and you had the formula for HBr. In letter B, CH3F, carbon contributes 4 valence electrons. There's 3 hydrogens for a total of 3, and fluorine, the halogen, will contribute 7. That gives us 14 dots by the time we're done drawing. You picked the least electronegative element to be the central atom. Never pick hydrogen, never pick a halogen. And you attached back all of the other atoms to the carbon. And when you did so, you tallied that you used 8 electrons to make 4 single covalent bonds, leaving you 6 dots left. And then I'm sure you placed those 6 dots around the fluorine. All done. Letter C, H2O2. Hydrogen each contributes 1 electron, but there's 2 of them. Oxygen contributes 6 electrons, and there's 2 of them. That gave you 14 dots altogether. Knowing that we cannot place a hydrogen between 2 atoms makes no sense because hydrogen can only have 1 bond. You didn't fall for that. You knew that the oxygens would have to be connected together. That an oxygen connected to a next oxygen, and then you would attach back, always thinking symmetry. Hydrogen can only have 1 bond, so that made them go on each side of the oxygen. There's your H2O2 using all 14 electrons. Oxygen, 2 sets of dots, 2 bonds, just like it wanted to have. I'm going to clean that up. 1 bond, 1, 2, 3, 4. There, we got it. So just to emphasize, we know oxygen wants to have 2 bonds, 2 dots. 2 bonds, 2 dots, and each hydrogen now has its 1 bond that it has. Perfect, I'm sure you're doing great. Let's look at D. N2H4. Nitrogen lives in group 5A, so we know it's going to contribute 5 dots for a total of 10. Hydrogen with its 1 valence electron, contributing a total of 4. We get 14 dots. We know that the nitrogens need to connect to each other because we know that hydrogens cannot have more than 1 bond. So just by connecting them together, we've used 2 dots. Alrighty, now we have 4 hydrogens. So let's remember too, what we're trying to say is nitrogen needs to have 3 bonds and 1 set of dots. That's what it wants to have. So as I think about attaching the hydrogens, think symmetry. I'm going to place them evenly so that you see that nitrogen each received 2 hydrogen. And what did we use? We used 1, 2, 3, 4, 5, 6, 7, 8, leaving us 4 electrons left. 1, 2, 3, 4. Each nitrogen has its 3 bonds and 1 set of dots. Each nitrogen, 3 bonds, 1 set of dots. You drew the Lewis dot structure, connecting the nitrogens together and using the hydrogens to complete the bond requirement. C2H6 came next. Yep, C2H6. We know that carbon has a 4 bond requirement. We know that hydrogen can never be, it makes no sense to try to put a hydrogen between a carbon because there's too many bonds there. So you must connect the carbons together. Carbons with its 4 bond requirement, I'll take the hydrogens to complete each of those carbons 4 bonds, and we've got it. There's C2H6. And letter F gave us CH2Cl. 2 hydrogens, 2 chlorines. The least electronegative element, carbon. Never put hydrogen, never put a halogen. I'm going to satisfy the carbon bonds by placing all of those around, remembering to complete the octet with all of those electrons that chlorine requires. Remember, carbon has 4 valence electrons. Hydrogen will contribute 1, but there's 2 of them together. Chlorine has 7 valence electrons, giving us a total of 14 dots. That gave us 20 dots to make our structure. 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20. Hey, we used them all creating our dots. I hope that's getting easier and easier. You know, a next set of problem I wanted to look at with you coming from your homework, where they give you kind of an attachment idea and just said, fill in the bond requirements given the arrangement of the atoms. So this becomes, I think, even simpler. And I'm just reminding us, hydrogen needs 1 bond. Carbon needs 4 bonds. Oxygen needs 2 bonds, 2 dots. Knowing those basic rules, we can start to connect these structures very quickly. In other words, I know that I've got to first of all connect all of the atoms with a single bond, right? They have to be at least attached by a single bond. Now, when I look at the hydrogens, they're done. This oxygen can get its 2 dots and 2 bonds by adding 2 more sets of lone pairs. And to get this carbon to have 4 bonds, I can see that it requires a next bond and the 2 dots on the oxygen up above. We've satisfied every requirement. Carbon with 4 bonds, check. See how we did that? Here's the 4 bonds around carbon. Perfect. Oxygen requires 2 dots, 2 bonds. Oh, we got it there. And we got it here. 2 dots, 2 bonds, the oxygen requirement. And lastly, of course, each hydrogen has 1 bond attached to it. So just thinking about how easy that becomes when you let the periodic table guide you into the number of dots and the number of bonds, spending that critical time we did in the first lesson together. And so I think you have some opportunities to do that, in a little bit of your homework assignment as well. And this is interesting. Here's an example from your homework where you're actually given a ball and stick model, and you're asked to convert that to a Lewis dot structure. And so really just understanding that the oxygens are in red, and if you're printed out in a black and white, it might be hard to tell, but the oxygens are the red. You know that carbon is always modeled with a black molecular atom there. And then, of course, the hydrogens are the gray or the white kind of molecular model kit ball there. So I would see, let's start here. That's a carbon attached to 3 hydrogens. And it's leading to an oxygen. That's where I'm at now, which then leads to a carbon who's double bonded to an oxygen. That's this part. I can see that it's leading to another carbon. Oop, and there's a hydrogen. Double bonded to a carbon, coming out as a hydrogen. Single bond, double bond, oxygen, CH3. So just by kind of following that all of these are oxygens, these are hydrogens, these are carbons, I'm able to just go through and connect the atoms. Now I want to carefully consider, especially for oxygen, I want to make sure it has 2 bonds, 2 dots. 2 bonds, 2 dots. And here's another set. And finally there, 2 bonds, 2 dots. Okay, we're back in action. I had to pause there for a moment. So here all of a sudden we've just had an opportunity to practice putting bonds and dots from a molecular model. And sometimes your homework is going to show some connectivity and just ask you to finish. And so I just wanted to share all the different varieties of homework type questions. And so for instance, in letter A, let me just model this one. I'm going to separate these so it makes a little better sense. I don't want all those atoms to come together. Letter A gives me 1 carbon, 5 hydrogens, and a nitrogen. And just ask me to draw the structure and make sure it's valid. So I'm just going to emphasize, here's what we know. Hydrogen, 1 bond, and it's done. Carbon requires 4 bonds, no dots. Nitrogen requires 3 bonds, 1 set of dots. And that completes the octet for each atom. So first of all, obviously, every atom has to be connected by at least a single bond. There has to be an attachment there. Alrighty. Now, what's left to consider? Well, hydrogens have each got their 1 bond. As a matter of fact, carbon has its 4 bond requirement. The only thing left to repair is the nitrogen. It has its 3 bonds, but it needs a set of dots. And that's all there is to that problem. Connect them, and then decide if anyone receives extra dots. Here's HNO2, nitrous acid, HNO2. I know the first thing I need to do is to connect everybody. Oh, you know what? This makes no sense. I am so sorry. That hydrogen, see how I did that? That hydrogen belongs to the compound below. No wonder it didn't make sense. I can't have 3 bonds on a hydrogen. On an oxygen. Let me redraw. H-O-N-O. That's all we were given in letter B. Got it. Okay, that helps me because otherwise I was breaking rules with oxygen. First thing we're going to do is to make sure everybody's connected by at least a single bond. I know oxygen requires 2 bonds, 2 dots. So I can satisfy this oxygen, 2 bonds, 2 dots, and I've satisfied this hydrogen with just its 1 bond. Right now, this oxygen and nitrogen don't have enough bonds. That lets me recognize there needs to be a double bond, a set of dots, and see what we've done there. Here's 3 bonds, 1 set of dots on the nitrogen, and I need to repair this guy. There's oxygen's 2 bonds, 2 sets of dots. And that completed the structure following the bonds and the dot requirements for each of our atoms. Let me clean it up just to redraw so you can, it's oxygen, nitrogen, then another oxygen. We completed everybody's lone pair just like that. Perfect. Letter C. C3H4. All right, so now I can see where I can attach everybody by at least a single bond. And then examine, have we met everyone's requirements? I noticed that this carbon, this looks good. It's got 4 bonds. He's happy. This carbon right now only has 2 bonds. This carbon right now only has 2 bonds. So that's not done yet, is it? All right, so if I look at that again and I see that hydrogens are good, this carbon here, we had a single bond. I know that doesn't make sense. That's my clue that we're going to need a multiple bond in there. And a multiple, to get each carbon, the 4 bond requirement will require a triple bond. So when I connect those atoms, each hydrogen only allowed 1 bond. Perfect. This first carbon has now 4 bonds. Perfect. But it leads out to a next carbon, leading out to a terminal end hydrogen. There's your structure that meets the bond requirements for each of those atoms. All right, great. Welcome back. I'm glad you had a little rest. We're going to look at applying some of our skills of drawing Lewis structures, just to include some of those polyatomic ions from last chapter. We're working with a polyatomic ion chart, remembering that those are groups of atoms acting as a unit carrying a charge. Those were on our polyatomic ion chart from last chapter. Groups of atoms acting as a unit carrying a charge. And I just want to kind of give a prospect of how to go about tackling those with these following examples. There, I'm catching up my definition. There we go. Groups of atoms acting as a unit that carry a charge. You can find each of these on your polyatomic ion chart provided to you as a test-taking tool from Chapter 3. For example, cyanide. Cyanide is a polyatomic ion. It has a carbon covalently bonded to a nitrogen, carrying a -1 charge. Notice that the -1 means that it has 1 extra electron. And so when carbon, who has 4 valence electrons living in group 4A, nitrogen, who has 5 valence electrons living in group 5A, and then notice that the -1 charge means that you have an extra electron, you get to add an extra electron to this dot structure that you create. So cyanide is going to be built with 10 dots, 10 valence electrons. Of course, we would know that the carbon and the nitrogen bond together. And so there's using the first 2. We would see 1, 2, 3, 4, 5, 6. And then if I used 7, 8, there would be no dots left. But clearly I see that I have some work left to do, because I know carbon has a 4 bond requirement. Nitrogen, 3 bonds and 1 set of dots. And clearly that's not this structure. And so when I bring in the nitrogen's electrons, I still have carbon with 2 dots, leading to a triple bond, leading to the nitrogen. And then since this is an extra electron, what you'll always see is this is going to be placed in a bracket and the charge outside. This is a polyatomic ion. Now I know what you're saying. Hey, I thought that cyanide had a 4 bond requirement, and it certainly does, the carbon. But remember, it's an ion, and ions have first names. So perhaps we have it attached to a hydrogen cyanide. Or perhaps we have it attached to, some other element. You could see then that it creates a site of attachment for what it's looking for to create an electrically neutral compound. So the cyanide itself is looking to complete its carbon requirement. That's why it's an ion and not a molecule. Phosphate, PO4, 3-. That tells us phosphorus, who lives in group 5A, oxygen, who lives in group 6A, and we have a -3 charge, telling us that we get 3 extra electrons when building. So that becomes 8, that's doing math, that's 26 electrons by the time I'm drawing phosphate. So phosphorus, reaching out to each of those oxygens, that used 2, 4, 6, 8. 16 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I didn't add that right. Oh, here's my mistake. There's 4 oxygens. Linda. All right, so thank you. I'm just working out and I ran out of oxygens. Would it be all right with you if I just retallied quickly? Because when there's 4 O's and not 3, we get all kinds of different numbers. Oh my. Thank you for your patience. 3 extra electrons. Now I actually have enough dots to build the structure I'm trying to. This actually gives me 8. This is 32 valence electrons when added correctly. And we used 4 bonds, so that used 8, leaving us actually enough dots to complete each of the oxygens octet. 3 sets of dots is 6 electrons, right? So then we had enough to complete the octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 dots, leaving us 0. Then what you'll see is in a bracket and the charge outside, that's the polyatomic ion phosphate. Ammonium has a +1 charge. So what that means is that nitrogen, who's contributing 5, hydrogen, who's contributing 1, and it had a +1 charge, meaning it lost an electron. So I actually have to subtract an electron from my total. So 9 minus 1 is 8 dots available, which is perfect. We'll have nitrogen connected to all 4 hydrogen, and because it's a polyatomic ion, you'll see that positive charge outside. Hydronium, H3O plus. Oxygen with 3 hydrogens, 1 set of dots, and a positive charge. Hydronium, H3O plus. Now, notice that when you have positive and negative ions, sometimes what you're seeing is that you don't follow that predicted pattern. Phosphorus. This is the pattern I would predict being in group 5. It's not following that, and that's why it has extra charges. Nitrogen, I would predict 2 sets of, or 3 bonds and 2 dots, and the bonds are not following that. That's why you see a charge on it. Oxygen, I would predict 2 dots and 2 sets of bonds, but it's not following that in the ion, and that's why it's carrying a charge. Polyatomic ions are kind of unique in the sense that we add or subtract electrons based on the charge, but then don't be mad when we don't follow the exact rules, because their ions are looking to change their bonds by attaching to something else. Hey everyone, me again, Mrs. Hanson, with some wrap-up information, some last topics in Chapter 4. Some of these words we've already been alluding to earlier when we were drawing Lewis dot structures. I was talking about picking the least electronegative element to place in the center of your Lewis dot structure and attach back all of the other atoms to it. And finally, I'm going to define the term electronegativity. The electronegativity of an element simply tells me about the atom's ability to attract electrons towards itself in a shared pair of electrons in a covalent bond. It tells us, in other words, how much a particular atom wants the electron, right? So how attractive are you in gaining electrons toward yourself? So think about increasing electronegativity, and we have the strongest of strong nonmetal over here, fluorine. Fluorine is the most attractive element to electrons. It's the strongest of strong, the most attractive nonmetal, gaining electrons, pulling electrons towards itself. So the closer you are to fluorine, the more you have an ability to draw electrons towards yourself. Let's explain why. Remember the atom of fluorine with its atomic number 19 is its mass number, just to try to think about what it's got. It's got 9 positive protons. It's got 10 neutral neutrons. And if you just think about the arrangement of electrons, they're giving an outer arrangement of 2, then 7. We have 2 valence, 2 shells, if you will. 2 energy levels, would that be a better word that we're used to hearing? 2 energy levels, period 1, period 2. Now with 9 positive protons and only 2 shells kind of protecting those protons, these protons are the most exposed, and that's what's going to draw electrons towards itself, right? Exposed protons draws electrons. Now think about what I'm saying. If we have fluorine with 2 valence shells around its, period 2, then if we go down a period, we've got chlorine and it's got 3 valence shells. That's why it's getting bigger. Bromine has 4 valence shells. That's why it's getting bigger. Iodine has 5 valence electron shells. That's why it's getting bigger. That those protons become more and more shielded and less likely to be able to attract someone else's electron towards itself. So these protons are least shielded by the electron shells covering it. Fluorine with its 9 protons. Of course, oxygen is small, but it only has 8 protons. Nitrogen is small, but only has 7 protons. More protons, the more ability it has to draw electrons towards itself. So fluorine is the strongest of strong nonmetal. Notice the trend. Electronegativity increases as you go up and increases as you go across. Fluorine, the strongest of strong. You can also just draw an arrow like this. That's the trend. The closer you are to fluorine, the more electronegative you are. And I placed one of these in here for you in your notepad. And I don't really think you rely on the numbers so much as you rely on a trend. The closer you are to fluorine, the more electronegative you are. If you rely on the trend, you'll be able to predict the answers without having to know these specific numbers. If we look at electronegativity as it increases across a row and it increases going up a column as atoms get smaller, with fluorine being the most electronegative element. Just use those trends really without even understanding the numbers. You don't have to memorize those, but just use the trends. Rank the following atoms in order of increasing electronegativity. So increasing means lowest to highest. And of course, highest would be who's closest to fluorine and who's the furthest away. So let's look at number 1. We have lithium, we have sodium, we have hydrogen. We know that electronegativity increases as you go up a column. That's our trend that we just wrote in our notes. Increases as you go up. So the lowest would be sodium. It's the largest atom. Its protons are shielded. Then lithium, then hydrogen. And you can verify that with your electronegativity numbers. But without the chart, that's what you're looking for. Don't rely on the chart. Understand the trend. It increases going up a column. Let's compare an oxygen, a carbon, and a beryllium. So now all of a sudden we're looking at the same row. And this is the trend. We have to work to remember that electronegativity increases towards fluorine. Furthest away, then carbon, then the closest, oxygen. Find the periodic trends. Next one we're examining, we're given chlorine, we're given iodine, and we're given fluorine. The trend, electronegativity increases going up a column. The least electronegative, chlorine in the middle, and then the most electronegative being fluorine. And one more trend, we have a boron being compared to an oxygen, being compared to a nitrogen. Left to right, boron, then nitrogen, then oxygen, increasing electronegativity as we read left to right on the chart. Well, these electronegativity values are used to determine the distribution of electrons in a shared pair called a covalent bond. So if the electronegativities of two bonded atoms are equal or they're similar, the bond is said to be non-polar. And I'm going to just define that as saying it's an equal distribution of electron charge in both directions. And that's really what our definition of a covalent bond is. So here we're writing down, good set of notes here. It says nonpolar. A nonpolar bond. A nonpolar bond means we have an equal distribution of electron charge. The electron clouds are evenly distributed to both atoms in the shared pair of electrons known as a covalent bond. Now, of course, if you have a like atom bonded to itself, the electronegativity difference is going to be 0. Electronegativity, En. The En difference of 0 means it's nonpolar. The other very common nonpolar bond that you should just remember is a carbon to hydrogen. The electronegativity difference is only 0.4 between a carbon to hydrogen. That's a very insignificant value for electronegativity differences, so that is also considered a nonpolar bond, a very small difference between C and H. That means that the bond has an equal distribution of electrons between the two atoms that are sharing the pair. So nonpolar bonds, an equal sharing of electrons, equally shared between two atoms. You need to remember any atom bonded to itself would have a 0 difference, and carbon to hydrogen is also a very common example of a nonpolar bond. If bonding between two atoms of very different electronegativity values occurs, we end up with what's called a polar covalent bond, or called a dipole. This is an unequal distribution of electron density. In the covalent bond, the more electronegative element is going to be able to pull the electron density towards itself, creating an area that's much more rich in negative charge and an area that is deficient in negative charge. For example, oxygen with its electronegativity value of 3.5 and carbon with its electronegativity value of 2.0. 3.5 minus 2.0 gives me an electronegativity difference of 1.5. The electronegativity difference is 1.5. That to me is a significant enough value to create a polar covalent bond. Covalent means it's still being shared, but not equally. And we start to see this symbol to denote a polar bond. Between the carbon and the oxygen, notice we have a little tail at the end of the arrow that looks like a positive sign. That tells me that the more electronegative element oxygen is very rich in electron density. This is a Greek symbol. It's a lowercase delta, just in case you wanted to know. In the Greek alphabet, in the lowercase Greek alphabet, it's a delta sign. Capital delta, lowercase delta. This means, the little delta sign means partially negative. And over here, this guy is going to be partially positive, just based on the unequal distribution of the electrons between the shared pair. Oxygen is stronger than carbon. It's so strong, it's pulling the electron density towards itself, creating a very rich negative region on the oxygen, and leaving the carbon a little it's a partial positive, my bad. Partially positive because it's lost its electron distribution. So when we have a bond where the pair that's being shared, a shared pair, is unequally distributed between the two atoms, we call it a polar covalent bond. The electrons in the bond are unequally shared. Those electrons are being pulled towards the oxygen, which is far more electronegative, and it gets this little Greek symbol to represent partially negative. And since the electrons are being pulled away from the carbon, the less electronegative element is going to be left with a partial positive sign. So the polar bond gets a symbol, and then the area in the molecule also gets those symbols. And let's put it together in terms of a quantitative value. In the left column, we see an electronegativity difference, which you often see just abbreviated as EN, electronegativity difference. If I subtract two elements that are in a bond together and get less than 0.5 for an electronegativity difference, we're going to call that a non-polar bond, and that those electrons are being shared equally. A moment ago, I gave an example of a carbon to hydrogen bond. The carbon, with its electronegativity value, we said was 2.5, and the hydrogen's electronegativity value was 2.1. When we subtracted that, we got 0.4 for the electronegativity difference. Well, certainly that's not a significant value. It's considered to be an equal distribution of charge between the two atoms. It's a non-polar bond. If we subtract two elements that are bonded together and come up with a value greater than 0.4, so let's say 0.5 to 1.9, just slightly less than 2, these are now called polar covalent bonds. Let's suppose I have a molecule that's, let's do HF. Fluorine with its electronegativity value of 4.0 and hydrogen with an electronegativity value of 2.1. When I subtract those two, that's 1.9. That's our electronegativity difference. And so clearly you see that that is an unequal distribution of charge, and you would represent that as a polar covalent bond, so much so that you'll start to see the electron distribution being pulled towards the fluorine. This is a very rich electron area, leaving the hydrogen as electron deficient and partially charged. So this would be called a dipole. It has a region that's partially positive and partially negative. A polar bond is formed. And then if we have kind of such a large electronegativity difference that the electrons aren't being shared at all, they're being transferred, we call that an ionic bond. So for example, if I were to have a compound built of sodium fluoride, NaF, sodium with its electronegativity value of 0.9 and fluorine with 4.0, when I subtract 4.0 minus 0.9, we get 3.1. Clearly, that's bigger than 2, so this is now an ionic bond. We knew that. It's a metal to a nonmetal, a positive and a negative. So we already suspected it was ionic based on the fact we had a metal with a nonmetal. And again, rely on the trends that we know more so than worrying about memorizing electronegativity values. Using these values, calculate. If you need to, we could just calculate or rely on trends. Are they nonpolar, polar, or ionic? So let's model HF. We said this a moment ago. We calculated hydrogen with its 2.1, fluorine with its 4.0. When I subtract the 2, I got 1.9. We called that a polar covalent bond. And I even drew that saying, boy, this is so polar covalent. Hydrogen is left partially positive, and the fluorine is partially negative. But we knew it was covalent because it's 2 nonmetals. Right? Nonmetal to nonmetal makes a covalent bond. Next one is MgO, magnesium oxide. Magnesium, 1.2. Oxygen, 3.5. .3 is our electronegativity difference. Well, that definitely falls in the ionic bond. But you know that. Rely on your lessons so far. A metal to a nonmetal is an ionic bond. Magnesium doesn't share its electrons. It wants to just give them away, and oxygen will take them in. Letter C, we have a fluorine bonded to itself. Clearly, electronegativity difference is going to be 0 when I subtract an element from itself. So this is a nonpolar covalent bond. ClF. When I'm bonding fluorine and chlorine, the electronegativity difference is 1. So this is also a polar covalent bond. 2 nonmetals, polar covalent. Water is attached as HOH. So the bond there is a hydrogen to an oxygen. Oxygen with its value of 3.5, hydrogen with its value of 2.1, we get 1.4. That is a polar covalent bond. 2 nonmetals, we knew it would be covalent. And here's ammonia, we've drawn several times. So it's an NH bond. Nitrogen to hydrogen, 3.0 minus 2.1. This comes out to be polar covalent. Relying on the trends and making sure that you see metal to nonmetal, ionic. Nonmetal to nonmetal will be covalent. And if it's a difference in polarity, it's polar covalent. And 2 elements that are similar, such as a fluorine to fluorine, or even a carbon to hydrogen, you can count that as nonpolar. Try these on your own. Will they be a pair of elements as polar covalent or ionic? Now I know it says using electronegativity values, but you can just rely on the chart and what we know, metal to nonmetal, ionic. Nonmetal to nonmetal, covalent. Let's see if that falls. Let me finish writing that. Let's see if it falls true. So hydrogen, 2.1. Bromine, 2.8. That's an electronegativity difference of 0.7. That's polar covalent. We knew that. Nonmetal to nonmetal. Nitrogen, 3.0. Carbon, 2.5. Electronegativity difference of 0.5. That falls as polar covalent. So we knew that. Nonmetal to nonmetal. Let's see, how about sodium and sulfur? 2.5 for the sulfur, 0.9, 6, 1. That's a little tricky there. I would definitely say that falls in the polar covalent realm because it's not bigger than 2. And then lithium and oxygen. Let's see, oxygen 3.5, lithium, oh yeah, here we got one there. This is ionic because it's bigger than 2. Alrighty, so we had one tricky one there. We had to rely on the electronegativity values. So perfect work there. We're getting the hang of this.